A critical component to mapping out the network traffic inside a UCS environment is to fully recognize that we have two separate, distinct fabrics. We have Fabric A, run by Fabric Interconnect A, and we have Fabric B that's run and managed by Fabric Interconnect B. So in this video, we want to take a look at two different concepts. First of all, intra-fabric communication, in other words, communication that stays within a fabric, but then also inter-fabric communication, so when we have network traffic going between the two fabrics. Let's take a look. So here we have the beautiful UCS architecture that we've been walking through with fabric interconnects and I/O modules, and we know at this point that we've got a virtual interface card inside of our server that's going to present multiple VNICs. At this point, we recognize that we're going to leverage VN tag on these VNICs, and so when we send traffic up to Fabric Interconnect A on this interface, it's able to tell which source that it came from. In other words, VNIC 1 might have a tag of, let's just say, 101, and VNIC 2 maybe has a tag of 102. We're able to do this because our VIC is operating in what we call adapter FEX mode. It's essentially a fabric extender for the upstream fabric interconnects, and so it's telling the fabric interconnect, hey, this is the virtual interface, so to speak, that it came in on. And the fabric interconnect is able to match that to a VETH port. This virtual Ethernet interface, let's just say this is virtual Ethernet interface 201, that's going to get mapped to this tag of 101. The identifier doesn't have to match the virtual Ethernet identifier, so I'm just trying to make that clear here. It could match. But either way, we're going to have a couple of virtual Ethernet interfaces in this case. Let's say we have virtual Ethernet interface 202, and that's going to map to a tag of 102. Now, I drew the VIC this way for a reason. Remember, we have a single virtual interface card in a server, and so we're going to have VNICs that attach two different fabrics. And so in our case, VNIC 1 and VNIC 2 are currently mapped to Fabric A. However, VNICs 3 and 4 are currently mapped to Fabric B. As such, we're going to have a pair of virtual Ethernet interfaces over here. Let's just call these 203 and 204. And so we're going to map our tags to them. Let's call these tags 103 and 104. And so our tag 103 gets mapped to virtual Ethernet 203, and VETH 204 gets tag 104. So when a packet arrives, the Fabric Interconnect strips off the VN tag, figures out which virtual Ethernet port that the traffic belongs to, and then we apply the policy and we switch according to that virtual Ethernet interface. Remember, this virtual Ethernet interface is treated exactly like a physical Ethernet interface. There's no difference to the Fabric Interconnect. Now, one thing we need to start to recognize here is that we have very distinct fabric paths. For example, very importantly, we never connect our Fabric Interconnects to each other, nor do we ever do a full mesh of connectivity to the I/O modules. The network engineers in us wants to do this, right? We're trained to deploy full mesh networks for redundancy. However, the redundancy comes from the distinct fabrics themselves. This concept comes to us from the fiber channel world. And while we are going to explore more about fiber channel in future parts of this course, namely in Domain 3, we do need to understand that this fiber channel world is an air-gapped topology. And the reason we have an air-gapped network is because we need resiliency inside of our storage area network. Fiber channel was built with this in mind. Fiber channel was built to connect to our storage. And if we think about the fact that we moved the hard drives out of our servers and onto the network, well, imagine if we lose network access to that storage. That would be basically like saying, okay, this PC that I'm running on right now has a hard drive in it. What if I just reached in there and disconnected that hard drive? How would that go for the PC? My PC would probably stop working. And so would the servers if they lose network connectivity to their storage. So resiliency is king in the storage area networking realm. And this is why we have the concept of an air-gapped network. And this concept becomes even more important in the UCS realm because remember, we're running native fiber channel over Ethernet down from the fabric interconnects. And therefore, we are able to deploy virtual HBAs into this environment as well. And as such, we must respect the air-gapped nature of fiber channel inside of UCS. In other words, Fabric Interconnect A is going to have a connection up to Storage Area Networking A. And Fabric Interconnect B will have an uplink to SAN B. And we're not connecting SAN A devices to SAN B devices because that would destroy the nature of our air-gapped topology. And so what we find is that we have a distinct path for our virtual HBAs to get up to their respective fabrics. Now, just to clean this up a little bit and get back to the Ethernet world, we recognize that that now applies to Ethernet as well. Because as mentioned, we don't connect our fabric interconnects together, and we don't connect our IOMs to two different fabric interconnects. And this is why we need to start talking about the concept of inter-fabric communication. Because how would this VNIC right here, let's say we have a virtual machine that is going to send traffic up to this VNIC here on Fabric A. What if this virtual machine needs to talk to a virtual machine on the right that is connected to a virtual NIC that is connected up to Fabric Interconnect B? Let's think through how this is going to happen. This virtual machine is going to go through VNIC 1. It's going to travel up to the Fabric Interconnect. it'll strip off the VN tag, recognize that it's attached to Virtual Ethernet 201, and it's going to check its CAM table because a Virtual Ethernet interface is just like an Ethernet interface. Now, these Fabric interconnects, they're running in end host mode, and because of that, they don't actually learn MAC addresses upstream. Instead, we use the concept of pinning, and this Virtual Ethernet interface is going to be pinned to one of these distinct uplinks. So when that MAC address isn't found in the CAM table, it will simply assume that it's to be sent out the pinned link, which is correct. It'll get sent out the pinned uplink. Now, the local area network, whatever our device is upstream that's processing all of this, it should have a CAM table that has all of the MAC addresses for our virtual machines. And even if it doesn't have the MAC address information, it's going to use traditional flooding behavior. So either way, that frame is going to get forwarded down to Fabric Interconnect B, at which point we have a CAM table where we know where this virtual machine is, and so we simply forward it down to the appropriate interface with the destination VN tag added to the frame. At this point, the VIC receives it, sees the destination, understands that, okay, I've got to send this out down towards this virtual machine. So just to make our path abundantly clear, we are going up through the local area network all the way back down, and guess what? We were destined for a different virtual machine on the same VIC. This is quite the networking path, and so we need to think about what the ramifications of this might be. And the biggest ramification is right here. This traffic is going to traverse the local area network even though the originating virtual machine and the destination virtual machine are on the same server. And in some cases, we might not want that. Remember, these Fabric interconnects, these are line rate monstrosities. They're able to process 10 gig and 40 gig and even 100 gig on our modern platforms at line rate. Wouldn't it be lovely to keep some of these traffic streams, especially the larger ones like live migration, keep it on the Fabric interconnects and don't hit the local area network with that? So we're going to be taking a look at how we might want to engineer this traffic a little bit to take advantage of this and keep that traffic off the local area network where we can. So that's inter-fabric communication. What about intra-fabric communication? What if we have a virtual machine connected to VNIC 2 here, and this virtual machine needs to talk to this virtual machine on the same fabric? Remember, this VIC is operating as a FEX, and FEXs can't switch traffic locally. We can't do something like this where we keep the traffic inside the VIC. Instead, we're going to have to forward that traffic up to the Fabric interconnect in order to get switched on the Virtual Ethernet interface. Now, at this point, we check that CAM table, and we realize that we do have a MAC address entry. It's downstream on a different Virtual Ethernet interface. As such, we don't have to forward it to the LAN. Instead, we forward it back down to the I/O module, which forwards it down to the VIC, which forwards it down to the VNIC, which ultimately lands on the virtual machine. So just to be clear once again, our traffic flow is going to start from the VNIC, go up to the Fabric interconnect, and get rebounded down and directed out towards its destination VNIC. At this point, we see that the LAN isn't affected by this traffic flow. Because we stayed on the same fabric, we're able to stay within the Fabric interconnect. And that's going to become an important part of the traffic engineering conversation in the next video. So this is where the networking of UCS gets really fun, because we see that we have two distinct fabrics in the network, and that creates some interesting traffic flows. For example, we saw with inter-fabric communication between the two fabrics, we actually have to send that traffic up to the local area network to get switched down to the other Fabric interconnect. That's a result of having an air-gapped network between our two different Fabric interconnects and just all of the components all the way downstream. Now lastly, intra-fabric communication, that stays within the Fabric interconnect. But at the same time, it's going to traverse a VIC, which is operating as a FEX. It can't switch traffic. It's going to get forwarded up to an I/O module. That's operating as a FEX. It can't switch traffic. So it does have to go all the way up to the Fabric interconnect and back down, but it doesn't need to hit the local area network at that point. I hope this has been informative for you. I'd like to thank you for viewing.